Hello and welcome to yet another video of Cornerstones of Math. This is sort of a follow-up video to my previous video, which features this function ln x to the power 4 plus 1. But my previous video doesn't actually involve the integral of this function, since the problem can be solved without it. However, I was still curious whether this function can be easily integrated or not. And it turned out we can indeed carry out this integral with only basic level calculus. So let's see how it can be done. So the very first method we have to apply is kind of obvious. You may have learned that in order to integrate much simpler function ln x, you consider the integrand as 1 times ln x and apply integration by parts with u equals ln x and v prime equals 1. And we can do the same for this integral. That is, we let u equals ln x to the power 4 plus 1 and v prime equals 1. Then we have u prime equals 4x cubed divided by x to the power 4 plus 1 and v equals x. Therefore, we have uv x ln x to the power 4 plus 1 minus integral u prime v. So if you multiply this and this, the numerator becomes 4 times x to the power of 4. So this divided by x to the power of 4 plus 1. Now let's take a look at this rational function. Notice that both numerator and denominator are polynomials of degree 4. And here's the general rule when it comes to integrating rational functions. Before applying any integration formulas, first you must split the given function into two parts. That is, you must extract some polynomial part so that the remaining rational part becomes the rational function where the degree of the numerator is less than the degree of the denominator. In our case, the denominator is a quartic function, so the degree of the numerator can be at most cubic. The general method for this splitting is dividing the numerator by the denominator, but in our case, we can do it in a simpler way. Since we have 4x to the power of 4, we just write 4 times x to the power of 4 plus 1, and then subtract the excess constant part, so minus 4. So this part becomes minus integral 4 minus 4 divided by x to the power of 4 plus 1. And this one we can easily integrate, so we have x ln x to the power of 4 plus 1 minus 4x plus integral of 4 divided by x to the power of 4 plus 1. Now what do we have to do with this remaining fraction? Of course, there are no simple and famous formulas to deal with rational functions with quartic denominators. So we have to split this one into simpler, more familiar kind of rational functions that can be integrated, well, more easily. In that sense, let us think about the case where the denominator is a quadratic polynomial x squared plus ax plus b. We are only dealing with the case where the numerator has a lower degree, so the numerator can be expressed as a general linear function cx plus d. We can easily integrate the functions in this form, and I will show you how. Let us first think about how we should split this function. The denominator is x squared plus ax plus b. Hence, the derivative of the denominator is 2x plus a. Therefore, we want 2x plus a on the numerator, because then the function becomes f prime x divided by fx form, whose antiderivative is ln absolute value of fx. In this slide, we write 2x plus a here, then we have to multiply c over 2 here. Then we must subtract this constant, which is ac over 2, then remaining plus d. So we can write c over 2 integral 2x plus a divided by x squared plus ax plus b dx, and this constant minus ac over 2 plus d times integral of just 1 divided by x squared plus ax plus b. Here, the first part is c over 2 times ln absolute value of x squared plus ax plus b. And these are just constants, so we can just write it as a new constant k, then integral of 1 over x squared plus ax plus b. And as for the integral on the second term, we can integrate it by completing the square and using trigonometric substitution. So the bottom line is, we can totally integrate this, so let us try to obtain this form. In order for this method to work, we should be able to factorize x to the power of 4 plus 1 into two quadratic polynomials. But x to the power of 4 plus 1 is not factorable, so how are we supposed to do that? Well, it is not factorable if we limit the coefficients to rational numbers, but if we include irrational coefficients, then it is factorable. Here we write plus 2x squared to make a perfect square, then write minus 2x squared here. Then we have the perfect square x squared plus 1 squared, then minus square root of 2x squared, which can be factored into x squared plus square root of 2x plus 1 times x squared minus square root of 2x plus 1. So now we have x to the power of 4 plus 1 expressed as a product of two quadratic expressions. So as for the next step, let us investigate whether our remaining integrand 4 divided by x to the power of 4 plus 1 can be expressed as the sum of two fractions having denominators of x squared minus square root of 2x plus 1 and x squared plus square root of 2x plus 1 respectively. As for their respective numerators, we write ax plus b and cx plus d. Remember, I have just explained that these two functions can be integrated, so if we manage to find the coefficients a, b, c, and d, then we can integrate this. In order to determine coefficients, we reduce to the common denominator x squared minus square root of 2x plus 1 times x squared plus square root of 2x plus 1. Then on the numerator, we have ax plus b multiplied by x squared plus square root of 2x plus 1, then plus cx plus d multiplied by x squared minus square root of 2x plus 1. And here the denominator is equal to x to the power of 4 plus 1, and as for the numerator, the first part gives ax cubed plus square root of 2a plus b x squared plus a plus square root of 2bx plus b. And as for the second part, we have cx cubed plus minus square root of 2c plus dx squared plus c minus square root of 2dx plus d. So if we rearrange in descending order of x, first we have a plus cx cubed, then square root of 2a plus b minus square root of 2c plus d x squared, then a plus square root of 2b plus c minus square root of 2dx, then constant term b plus d. Therefore, comparing coefficients, we have a plus c equals 0, square root of 2a plus b minus square root of 2c plus d equals 0, a plus square root of 2b plus c minus square root of 2d equals 0, and b plus d equals 4. We have 4 unknowns and 4 equations, so this is solvable. Let's start with simple equations because they will easily allow us to reduce the number of unknowns. From equation 1, we have c equals minus a, and from equation 4, we have d equals 4 minus b. Substituting these into equations 2 and 3, we have, from equation 2, we have square root of 2a plus b plus square root of 2a plus 4 minus b equals 0. And from equation 3, we have a plus square root of 2b minus a minus square root of 2, 4 minus b equals 0. So we have 2 square root of 2a equals negative 4, and 2 square root of 2b equals 4 square root of 2. So we have a equals negative square root of 2 and b equals 2, which gives c equals positive square root of 2 and d equals 4 minus 2, hence 2. Therefore, the complete partial fraction is minus square root of 2x plus 2 divided by x squared minus square root of 2x plus 1 plus square root of 2x plus 2 divided by x squared plus square root of 2x plus 1. So now we return to our most recent progress, which is this step, and apply our partial fraction here, which gives integral of minus square root of 2x plus 2 divided by x squared minus square root of 2x plus 1 plus integral of square root of 2x plus 2 divided by x squared plus square root of 2x plus 1. And now we carry out each integral as I have previously explained. As for the first integral, the derivative of the denominator is 2x minus square root of 2. But since the original numerator has minus square root of 2x, we must multiply minus 1 over square root of 2 here, right? This gives constant term 1 here, so in order to make it 2, we must add 1 here. As for the second integral, we need the derivative of the denominator 2x plus square root of 2. And now this must be multiplied by 1 over square root of 2. Then we have constant 1, so we add 1. Therefore, the first integral can be split into minus 1 over square root of 2 times the integral of 2x minus square root of 2 divided by x squared minus square root of 2x plus 1, then plus integral of 1 over x squared minus square root of 2x plus 1. And the second integral is split into 1 over square root of 2 times the integral of 2x plus square root of 2 divided by x squared plus square root of 2x plus 1 plus integral of 1 over x squared plus square root of 2x plus 1. So this integral gives ln x squared minus square root of 2x plus 1, and this integral gives ln x squared plus square root of 2x plus 1, and then two remaining integrals. We don't need absolute values for the logarithms because both of these polynomials are positive for all real numbers x. Here, combining these two logarithms, we can write it as 1 over square root of 2 times ln x squared plus square root of 2x plus 1 divided by x squared minus square root of 2x plus 1, and then remaining integrals. Now let us complete the squares on these denominators to apply trigonometric substitution. Then this denominator can be written as x minus 1 over square root of 2 squared plus 1 over 2, and the next one is x plus 1 over square root of 2 squared plus 1 over 2. So as for the first part, we apply the trigonometric substitution x minus 1 over square root of 2 equals 1 over square root of 2 tangent alpha. And as for the second part, we apply the trigonometric substitution x plus 1 over square root of 2 equals 1 over square root of 2 tangent beta. Then we have dx equals 1 over square root of 2 secant squared alpha d alpha and dx equals 1 over square root of 2 secant square beta d beta respectively. And we have, so this squared equals this squared, so 1/2 tangent squared alpha, and combined with this 1/2, we can write the denominator as 1/2 times tangent squared alpha plus 1. Then dx part, 1 over square root of 2 secant square alpha d alpha. And similarly for the second one, we can write the denominator as 1/2 times tangent square beta plus 1. Then dx part, 1 over square root of 2 secant square beta d beta. Notice that tangent square alpha plus 1 equals secant square alpha, and tangent square beta plus 1 equals secant square beta. So we are only left with constants, which are square root of 2 for both cases. So we have integral of square root of 2 d alpha plus integral square root of 2 d beta. So we have plus square root of 2 alpha plus square root of 2 beta, and we finally have the constant c. So if we change alpha and beta back to x, we have our final answer, which is x ln x to the power of 4 plus 1 minus 4x plus 1 over square root of 2 ln x squared plus square root of 2x plus 1 divided by x squared minus square root of 2x plus 1 plus square root of 2 times, and alpha equals inverse tangent of square root of 2x minus 1, so plus square root of 2, and beta equals inverse tangent of square root of 2x plus 1, so this plus constant c. So this is our answer. So this was indeed a tough integral problem. But if we keep calm and use what we have in our integration arsenal, we were able to show that the integral can be done. And that was all for today's video. Thank you all for watching. Please don't forget to hit the like and subscribe buttons if you enjoyed this video, and I will see you in another video.